Right, it is 7 p.m. So for the sake of time, I think we'll go ahead and get started here. My name is Laura Hankey, and I serve the American Gelbvieh Association as an educational content coordinator. Um, Thank you so much for your time here this evening joining us. We are excited to present Genomics, Improving the U.S. Cow Herd, presented by the American Gelbvieh Association. We're joined here tonight by Dr. Matt Spangler, Professor of Animal Genetics and Extension Beef Genetics Specialist at University of Nebraska-Lincoln. Dr. Spangler will be sharing his research on genomics in the beef herd and how as seed stock and commercial producers can best apply genomics for herd improvement. Just a couple of quick housekeeping notes before we get started here tonight. Your mics are all muted. We've designated around 30 minutes here at the end of our webinar for Q&A. You can ask any questions that may arise by typing them into the chat box located at the bottom of your screen. Feel free to do that at any time during the program here tonight. Also, if for some reason we don't get to your question this evening, or you think of something after the webinar has ended, we'll be sharing a follow-up email with contact information for both myself and Dr. Spangler. And finally, if you would like to review this webinar, we'll be sending out an educational library link located at gelbvieh.com, and that will also be included in this follow-up email. So with that, I'm going to go ahead and turn things over to Dr. Spangler to get things started here this evening. Dr. Spangler, thanks for joining us.
Certainly my pleasure, and I appreciate the opportunity to visit with the group tonight, and certainly look forward to the questions at the end. So I put on this first slide my email address, and I'm fairly easy to find at UNL, but certainly encourage anyone that has questions over anything I do cover or don't cover relative to genetics and genomics to reach out to me. I wanted to start by just going through some definitions, because one of the most confusing things I think in the area of genomics is all the different words we toss around as if everyone knows exactly what we're talking about. And the first is, what is genomics? You can see the definition here, and I won't read it verbatim, but it's basically what's emerged as a newer, if you will, branch of biotechnology that's taken genetics and molecular biology and advanced that field, given that we have knowledge of the genome sequence of different species. And it really focuses on the generation of data, the organization of the data, and then the application of it. And certainly there's been application of genomics far outside of beef cattle, not only in different livestock species, but certainly in human medicine as well. So a few more terms: the genome, simply the genetic material of an organism. A chromosome, really you can think about something that harbors genes, and they occur in pairs in beef cattle. A gene, that's something really our definition has changed over time in the genomics and molecular biology arena. But you can think of it as a specific sequence of nucleotides and really a functional unit of inheritance. A locus is nothing more than a particular location in the genome. So locus is Latin for location. And so it's a particular spot in the genome. An allele can be an alternate form of a gene, alternate form of a SNP, or any other DNA variant. And then a SNP, which you hear a lot about, is a single nucleotide polymorphism. And what in the world does that mean? Single, so it's one nucleotide, one of those basic structural units of DNA, and then polymorphism, a change. And so we've been able to leverage knowledge of these single nucleotide polymorphisms to use as markers across the genome. And I'll talk with how we've been able to leverage that to actually improve beef cattle genetic selection. So for those that have been around genomics for a considerable amount of time, you'll recall the evolution of what I'd call the density, or the number of markers on available tests. So if we think about marker or SNP density on a test, being akin to mileage, then we can think about the distance from Washington, D.C. to Anchorage, Alaska, and that's about 3,300 miles. So if we have a DNA test that has 3,000 single nucleotide polymorphisms on it, I'd call that a 3K, so 3,000 marker panel. That's about one SNP or one marker every mile between Washington, D.C. and Anchorage. A 50K or 50,000 DNA marker test is a marker about every 100 miles. 700,000K or 700K test, 700,000 markers, is a marker about every 22 feet. So really, the number of markers on a panel or on a test is really a question of resolution. What I would tell you, though, is from a lot of research, from a lot of different institutions, including our own here at UNL, is it doesn't really matter all that much. So even though we get more resolution with more markers, the accuracy we see in EPD doesn't seem to be substantially impacted. What does matter is which markers we use, because some are more informative than others are. So genomics is just the new source of data, and I hate for people to think it's the only source of data. So if we think about what goes into our genetic predictions or EPDs, it's really based on kinship. So we leverage kinship among animals. Traditionally, that's been based on pedigree. So we can take advantage of records from relatives, records from an individual themselves. Now we augment that with genomic data. And should those animals become parents in a recorded herd, we get records from their descendants. And if you think about it holistically, what we're really doing is weighting these sources of information. So you can think about a really big selection index where every relative of an individual, their record is being weighted proportional to how closely they are related to the animal in question. And those records are also weighted by how heritable they are, right? But as I alluded to, not all data are equally informative. So, a record on a grandparent is not as informative as a record on a parent because there's greater distance in terms of kinship. Records are weighted proportional to how informative they are. And I'd say kinship goes into that, heritability goes into that, the genetic or variation among animals now via the genomic markers, genetic correlations among traits. So I can get an EPD for post-weaning gain or yearling weight because all I have is a birth weight record. And that's because there's a genetic correlation between birth weight and later growth traits. So we take advantage of a correlation among traits. I would also mention that we can also take into account the confidence we have in the records themselves. And that's something that IGS, which the American Gelbvieh Association is a partner of, actually does for the trait of birth weight. So here's an example of that. On the top left, you'll see birth weight records that are recorded with a digital scale. On the top right, you have birth weight records recorded with a hoof tape. Bottom left, ones that in this I called fabricated, but that suggests I know the intent. Let's just say that they were maybe not recorded very well. And then the bottom right is noisy. So you get things coming in a contemporary group. They're only in 10-pound increments, an example. So some organizations take advantage of artificial intelligence and deep learning, so machine learning algorithms to categorize data as to how it was generated. And based on that, it can be weighted in the analysis or in the generation of EPDs, because we know that Contemporary groups measured with a digital scale have more variation and have more information content than things that were perhaps measured in 10-pound increments, or things where, like on the bottom left, were clearly truncated and have reduced variation. I say all this to tell you that when you're dealing with clientele and they tell you, well, that stuff's just made up because I don't trust the data that goes into it. There are very sophisticated safeguards to ensure that the data is of high quality. Now, if we get back to kinship, which is really the backbone of genetic evaluations, as I've said, we traditionally think of that as pedigree. And kinship is critical for the prediction of genetic merit. Particularly think about sex-limited traits, something like stayability. We still get EPDs on bulls, and that's because of being able to have kinship, because it allows for this flow of information among relatives. And one thing genomics has helped us with very early on is correcting pedigree. So sire misidentification has been a substantial issue in a lot of populations, and I have estimates here in sheep of the proportion of misidentified animals, some in cattle, and then some in goats. And so having animals that have incorrect pedigree, and we often think about that as sire misidentification, but most certainly it can occur on the dam side too. It breaks the kinship ties, and it creates false ones then. And what happens is that decreases our estimates of heritability because we've broken kinship ties, and we're misassigning phenotypic information to relatives. Those two things, the misassignment of phenotypic records and the reduction in heritability, leads to incorrect EPDs, which can lead to incorrect selection decisions. And these impacts are the greatest if you have heavily used bulls that themselves had an error in their pedigree. So genomics has done wonders for being able to clean up pedigree errors. Just a simple example here, I wanted to talk through the difference between validation and testing, or what I might also call discovery relative to parentage. Validation asks the question, given a particular progeny, do the sire and dam on record qualify as parents? And traditionally, what's been used is a panel of between 100 and 200 DNA markers to answer that question. Some organizations have moved to using all 50,000 DNA markers to answer that question, and it's really exclusion-based. So allowing a certain proportion, usually about 1 to 2% of the markers that can mismatch between an offspring and a parent to take into account potential genotyping error, but then basically asking the question, could this offspring truly be the descendant of this sire and dam? Doesn't say it is for sure, but it says it could be. What testing or discovery does is it says, right, we have a calf. Now let's compare its genotypes to all possible sires in a particular database that are genotyped, and let's discover who the true sire is. Or of all possible dams in a herd, let's discover who the correct dam is. So that's a different way to use the genomic technology to assign parentage. And as populations like Gelbvieh get more and more genotyped animals, it allows this discovery process to actually occur. I wanted to make a point here that there is considerable variation in the number of calves produced in multi-sire pastures. So a benefit, of course, of genomics is not only correcting perhaps mistakes during AI, but allows you to turn out multiple sire cleanup bulls or cleanup pastures and know that you can correctly assign calves to sires later on. And in really big multi-sire pastures, we observe quite a bit of variation in the number of calves sired. And in fact, if you treat the the count of calves sired by a bull as a trait, the heritability of that's close to 20%. So there is a genetic component, and you can see here in 24 different contemporary groups, and this is from a large commercial herd in the Sandhills in Nebraska, there is a lot of variation in the number of calves sired by particular bulls. And so just another example of thinking you may turn out a couple of bulls and they're going to have an equal proportion of calves sired. That's not necessarily the case at all. So going back to kind of parent validation, very simple example of how that works. If we have 3 candidate bulls here, the A's and B's represent 2 different loci, so 2 different spots in the genome, and we're going to use those 2 spots to try to assign the correct sire to this calf. And again, in practice, we use far more than 2 genetic markers to do that. But given these 3 bulls, you could ask the question, well, who is the most likely sire given these 3? And if you go through and compare those sires to the calf at both loci, it's got to be bull B, because he's the only bull that could pass on both a big A and a little b to this offspring, to this calf. Now, the problem with this whole process is, what if there were actually 5 candidate bulls and you only turned in DNA samples on 3 of them? All we can test against is the 3 that are genotyped. We can't test against the other 2. So it's possible that one of the other 2 is actually the true sire. We just have no way of knowing because we couldn't do that comparison. So when you think about doing parentage testing, you need to make sure to genotype all possible parents. So if we step back before we talk about genomically enhanced EPDs and just talk about EPDs in general, we really learn about sires through their offspring. And apologies right up front, I was lazy and didn't put pictures of Gelby in here. There are some later on, but this one clearly isn't. This bull, if we assume he had these 5 calves and they come from different herds, right, just completely different contemporary groups, we can compare those calves to the average of their contemporaries. And so this calf at the top weighed 30 pounds more than the average of his contemporaries, and the calf in the middle weighed 10 pounds less than the average of his contemporaries. So we get a sense for how, on average, this bull, how his calves compare to the average of their contemporaries. And that kind of becomes a foundation for determining the expected progeny difference, or EPD, of this bull. An important note, though, is the offspring of a single sire will exhibit more than 3/4 of the diversity of the entire population. Another way of saying that is knowing the sire only accounts for about 1/4 of the additive genetic variance. What does that mean practically? It means if you want to increase the uniformity of your calf crop, or your bull buyers do, and you tell them, well, hey, buy these 2 half sibs, right? They're more closely related. That surely ought to increase uniformity. What doesn't? Because those 2 half sibs could be dramatically different in their genetic potential for a number of traits. So in the quest to increase uniformity, the best option is to choose bulls that are more similar in their genetic values, or their EPDs, for the trait that you want to increase uniformity for. Because even closely related bulls, half sibs, even full sibs, could differ substantially in terms of their genetic values. And so before I explain exactly why that is, just a reminder that cattle have 30 pairs of chromosomes, 29 what we call autosomes, and then a sex chromosome. They get half of the pair from the sire, half of the pair from the dam. The entire genome of beef cattle is about 3 billion base pairs. So as people begin talking about whole genome sequence, they're talking about really getting the whole DNA sequence of an animal. and all of the DNA variants that encompass it. So now all of a sudden, we're not talking about tens of thousands or hundreds of thousands of DNA markers. We're talking about tens of millions. And so if we assume we had these three bulls here, and the top bull, if we assume this is a weight trait and for our purposes, higher's better, the top bull has the most desirable EPD, and the bull in the middle has the least desirable. Now, I also have on here EBV, that's estimated breeding value. EPD, expected progeny difference, is half of that. So an EPD is the genetic value of an animal as a parent. Breeding value is the genetic value of the animal itself, because a parent only passes on half of its genetic material to the next generation. That's why we make that division by 2 there. Each of these numbers represents the numerical value of the allele or the DNA variant at that particular spot in the genome. So if we look at this top animal, this -2 says that particular allele has an effect on the trait of a -2, so it's not good for growth. But what it inherited perhaps from the other parent is a +2. And so if we knew across the entire genome all of the alleles that had an impact on any trait we're interested in, and exactly what their effect was, this whole process becomes nothing more than addition. The problem is we don't know what all of those, what I'd call causal DNA variants are, much less what their effect is, right? So that's why we have to make estimates. The other thing I'd like to point out from this slide is that it's possible for that really good bull that has the better EPD to have bad calves. And that's through this process of Mendelian sampling. You can imagine the bull on the top, when he sires a calf, passes on a sample of his worst possible genetics. He passes on the -2, the -3, the -4, etc. And it's also possible that this really bad bull produces a decent calf because through Mendelian sampling, he passes on the best possible sampling of genetics he has. But on average, these values, the EPDs, hold true, right? So it's important not to compare them in isolation, one calf. You have to compare them in terms of group of offspring among sires. Now, if we think back about kinship, and then I'll get to how genomics influences this, I have a very simple 3-generation pedigree here. So based on pedigree, we would say the relationship between individual 1 and individual 10 is a quarter, 25%. So we expect an individual to share 25% of their genetic content with a grandparent. So just like you and a grandparent. But that's our expectation. That's an average value. That value could actually range between 0 and 0.5, assuming no inbreeding. And I didn't see the list of people on the webinar, so I'm going to assume no inbreeding amongst you as well, as you think about the relationship between you and a grandparent. But what happens if individual 1, or pardon me, what happens if individual 7 passes on everything that it received from animal 1 to its offspring, which is animal 10? Now, all of a sudden, that creates a 50% relationship between individual 10 and its grandparent. Or individual 7 could pass on everything it got from individual 2 onto its offspring, in which case that creates a 0 relationship between individual 1 and 10. On average, it works out to a quarter, but on an individual by individual basis, it can certainly vary. And it is in that variation that we're able to leverage genomics and determine more accurate representation of the relationship among individuals, and as a consequence, do a better job at estimating the genetic merit of individuals because we're more correctly weighting the phenotypic information according to the kinship among animals. This is a real example. This is actually pig data, but it works the same in beef cattle. These are genotypes, 50,000 DNA marker genotypes among individuals and their grandparents. And the red vertical bar is right where our expected value is at 25%. But you can see a range from about 0 to a half, and it's a very nice bell-shaped curve. So that's what we've always known theoretically to be true. And genomics has allowed us not only to observe that, but also leverage it. This on the vertical axis there shows you BIF, or Beef Improvement Federation accuracy, and how that is impacted by different sources of information. We start off with the pedigree estimate, nothing more than sire plus dam divided by 2. Maybe an individual has their own performance record. We genotype them. And then eventually, if they become a seed stock animal, they have progeny. What I want to impart here is that we cannot continue to build accuracy, even with genomics, if we don't continually record phenotypes. You notice you don't see big jumps in accuracy again until individuals, sires, an example, have progeny, and that's progeny with phenotypes recorded. So even if you invest in genotyping, you need to continue to collect phenotypes just as you always have, because genomics tells us nothing without something to relate it to, and that something is the phenotypic records. So phenotypes are always going to be king. Genetic evaluations will be best if there's a continuous flow of phenotypes. And so if we think about emerging traits, be it pulmonary arterial pressure for those that are at altitude or sell bulls to altitude, foot and leg scores, mature cow weight, carcass traits, we need actual phenotypes, and we need a continuous flow of them. And I put here the best way to tackle novel traits, those that aren't recorded as densely, is to make them less novel, right? So genomics isn't going to solve that itself. We have to be able to collect phenotypic records. And I would point out that quality phenotypes near selection candidates, near the animals we really want to sort among, are the most important. So just because a bull's great-great-grandfather had feed intake data recorded, that doesn't do a lot. I really need his sire to have feed intake data recorded. And ideally, I'd like him to have feed intake data recorded, right? So data close to the animals we really care about sorting among is the most important. This just illustrates accuracy again. Here I have Beef Improvement Federation accuracy is BIF. That's the one in the US for beef cattle we use. 3 different heritability levels of traits. So heritability of 0.1 would be like fertility traits, 0.3 like growth traits, and you get up to 0.5, that's like mature cow weight. If you think of something that's lowly heritable like female fertility, before a bull gets proven, he's got to have hundreds, if not thousands, of daughters out in production with those records. So what genomics has enabled us to do is to really get a higher level of information much earlier in life, so we can make better decisions and make faster decisions. So here's my Gelbvieh picture, and if you don't like it, the blame goes to Oklahoma State's breed website. I figured that was the safest place to grab one. I'm going to talk about accuracy in a different way here. Got a calving ease direct EPD of 9, low accuracy EPD, so yearling bull, it's 0.2. We can use what's called possible change to determine a confidence interval around that bull's EPD. So given the trait of calving ease, given the accuracy, we can look up what's called his possible change value. And we can say, well, we're 68% confident his true EPD is between 2.8 and 15.2 in this example. And all I've done there is taken his EPD and subtracted off the possible change value, that's the lower bound, and then added the possible change value, that's the upper bound. What if, though, we DNA tested this bull and jumped his accuracy up to 0.4? Now what we've done is really narrowed up that window, right? So that's the benefit. We've narrowed up the window where his true genetic value actually is. So that's another way of thinking about how we've made his EPD more accurate and how we can have more confidence in it. This is, I think, the only equation I showed, and it's what we call the breeder's equation. So the delta breeding value, or the change in genetic value we make per unit of time, is a function of the accuracy of the tool we use to select. The little I is selection intensity. How choosy are we in selecting the parents for the next generation? Do we only pick the top 1%, or do we take the top 10%? The amount of genetic variation in the trait. And then in the denominator, the L is the generation interval, the average age of the parents when the next generation is born. In beef cattle, that's anywhere between 4 and 6 years, typically. And so by genotyping animals, we increase the accuracy, but we do so at a much younger age. Typically, to increase accuracy, it takes time. Animals have to get older, have offspring. Now we can do it before they have offspring. So that allows us to make faster rates of genetic gain, and that's the real benefit to seed stock producers. To commercial bull buyers, it's all about mitigation of risk, knowing that you're buying something with more confidence. Of course, those that have genotyped for a long time understand the comment I make on the bottom of this slide. Increased accuracy doesn't mean the EPD move in a favorable direction. It means they get more accurate, which means they could move up or they could move down. And in population wide, we expect about half of them to move up and about half of them to move down, right? So if you make the investment for the first time and say, well, my favorite one got worse, well, view it as a good thing, because now you know it's not as good as you thought it was. Oh, another point, that's why you do it before you put together your sale catalog, right? Genomics is meant to help you make decisions. If you do it after the decision's already been made, then you're really not getting a return on your investment. Yet another way to look at the impact of accuracy is what we call progeny equivalence. AAA is Angus, AHA is Hereford, IGS, of course, International Genetic Solutions, of which Gelbvieh is a partner. I didn't mean this to compare across breeds, so please don't, because it's a bit apples and oranges here. But the point I want to make is if you take a trait like marbling and look at the IGS value, that says that I can genotype a non-parent bull and increase the accuracy of his EPD to the same level as if he'd already sired 8 calves that have actual carcass records. I think that's pretty phenomenal before a bull's even been turned out on cows. And this has really been leveraged by the dairy industry. Think about something like milk. It takes a long time before daughters go into lactation. So it takes a long time to learn about a bull's genetic value for milk yield and milk components. But now, before a Holstein bull ever breeds cows, they can have very high accuracy proofs on him for lactation traits. So a point I made earlier, how are genomic EPD being used? Well, if you're using them for selection, then you genotype every calf born. Bull calves, the heifer calves. Even encourage you to genotype the deads. And the reason I say that is it's a really nice way to be able to monitor for emerging genetic defects. Now, if you're just doing it for marketing, then you only genotype selected animals, right? You put the bull sale catalog together and you only genotype the ones in the catalog, or maybe you only do what you consider the front end bulls because they may have other breeder interest. You're really doing yourself a disservice, and you're certainly doing the breed a disservice because it reduces the amount of data then that we can actually use to make these genomically enhanced EPDs even better. And if you're not doing females, that makes it hard to have really impactful genomic predictions for fertility traits. Use just a practical example from our UNL seed stock herd. I have faculty oversight over that. We AI once, we turn out multi-sire cleanup bulls. We try to get TSU collection done at branding. Really like to do it at birth if I could, but reality is we rely on a fair bit of student labor, so there's a little bit more risk there when we're putting in mother up tags in the calves. So we do it at branding. That gives us another chance at weaning if we need to get another sample. I can only put about 90 bulls on feed. That's all we have room for. And I may have 120 to 150 bull calves born. So I got to make a decision. And genomics allows me to make a better decision at which bulls I promote to go on feed. And then again, which ones I promote to actually go into the sale. And, we make AI mistakes. And then, of course, with multi-sire pastures, right, there's uncertainty there. And so having all that straightened out early allows us to do a better job of getting sale catalogs put together. I want to just briefly touch on what I'll call novel traits you may hear in popular press or on the radio about genomics for disease susceptibility, more refined measures of female fertility, but also male fertility, feed efficiency, the microbiome, healthfulness of the meat product itself, the mineral content, the fatty acid profiles of it. All of these things, areas of either past or current research, and genomics has enabled us to really investigate what are the genetic underpinnings of this trait. In other words, how heritable are they, and are there large effect DNA markers that contribute to the variation for these kinds of traits? That said, as you hear about the microbiome of animals, which is really the community of bugs, if you will. So an example, bacteria that inhabit the ruminant beef cattle, inhabit the ocular space of beef cattle. They inhabit us as well, right? That's the microbiome. That indeed is heritable. You may have heard of epigenetics or methylation. Methylation patterns in beef cattle are also heritable. And we've shown that clearly here at UNL, that both those things are heritable. And the point I want to make by that is we hear that these new sources of information kind of explain everything, right? Well, if they're heritable, that says there's redundant information there. So if we know the genetics, we already know part, at least, of the microbiome. We know part of the methylation pattern in animals. So it's not completely new sources of information. Very exciting areas of research. But I think the power will come when we couple these new sources of data along with genetics/genomics to perhaps do an even better job of predicting than we are now. So key takeaways from this wicked twisted road, as it were: the study of genetics, and more specifically genetic evaluation of beef cattle, has been an evolutionary process that goes back several decades. And we continue to make, and we will continue to make, incremental steps at making these tools even more accurate. And as the tools evolve and become more accurate, the risk of not using them becomes even greater. If you're on this webinar and been on the sidelines about EPDs or genomics in general, I really think you're doing yourself a disservice by not completely jumping in. Genomic tools work, and they have a growing application in the seed stock sector. We use them to increase the accuracy of EPD. We can even use them to do a better job of tracking inbreeding. So I think there's a lot of application of genomics that we haven't fully utilized yet. I'd like to put in a plug for what I think is a very useful educational resource here, this Beef Sire Selection Manual. You can access that at ebeef.org, or if you want a hard copy of it, just shoot me an email. I'll mail you one at no cost to you. Then lastly, just a thanks. I mentioned ebeef.org, of course, our UNL beef production website, beef.unl.edu, all things beef cattle related. The Beef Improvement Federation website. If you haven't been to a BIF meeting, strongly encourage you to go. The one in 2024 will be in Knoxville, Tennessee. And then lastly, nbcec.org, the National Beef Cattle Evaluation Consortium. All of these you can find educational material on. The last one hosts a webinar series on over the noon hour Central Time on Wednesdays in October. And so that's coming up. But with that, I would be more than happy to entertain any questions over things I've covered or things I haven't. So thank you.
All right, thank you, Dr. Spangler. We do have some questions rolling in here. Before we get to those, I have a quick question. So thinking about the commercial producers as well as the seed stock producers that we have joining us here this evening, if you had to pick out top 3 reasons for a commercial producer to genomically test their herd, how would you rank those and what would they be?
Yeah, that's a really interesting question. And I'm gonna turn it around a little bit. And I'd say, what are the top 3 things you need to do before you consider doing that? And the first one is you need to ensure, if you're a commercial producer, you have a well-structured crossbreeding program. The benefits of heterosis are going to outweigh a lot of other things. Second thing you need to do is to make sure that you're doing sire selection correctly. And so you're actually investing in good genetics on the sire side. And then the third thing, which probably should have been the first thing, is that you have a well-formed breeding objective. So you actually know where you're going and you know where you sit now. If you can tick all 3 of those boxes, then you can contemplate as a commercial producer making the investment in genomics and commercial animals. If you can't tick those 3 boxes, then don't do it. Then you have to think about what's the return on investment. So the cost of the technology versus the decisions you will actually make. And there it goes to what's the accuracy of the selection decision for, generally you're talking about commercial replacement females. So it becomes an ROI question. If you can't figure out, I think commercial producers have to answer those first 3 in the affirmative before they ever consider genomic testing commercial animals. And I'm not confident, and I know the people on this webinar are the exception to what I'm going to say, but I'm not confident the lion's share of commercial producers can check all 3 of those boxes.
Very good, thank you. All right. Well, let's answer some questions here for folks on our webinar here this evening. So first question here, do we have data on what percent of Gelbvieh and balancer bulls are genomically tested before selling? That is one we will get back with you on. I am the only Gelbvieh rep on the call here this evening, and so want to make sure that we get you the correct information on that, Mark, and we'll get that right back to you.
I'd like to know the answer to that one too.
Very good, very good. All right, second question. Does the research show that InVigor score from Neogen is cost effective?
Yeah, so the InVigor score really meant to get at retained heterosis. So that the only, what I'd call it's quasi-independent research was actually on the people that developed that. That was actually developed in Canada. And Neogen acquired it when they made a purchase of a lab in Canada. And so that group actually did publish some research that actually showed that it was predictive of retained heterosis. But that was in, if I recall correctly, in their population of animals owned at the university in Canada. I have not seen independent research on a much broader population.
All right, very good. If I understand you correctly, any animal will have offspring 70% of the variability of the trait. How much is that reduced by line breeding?
Yeah, I'm going to need a little bit more detail there. So, uh, I think what the question's getting at is that sire, right? The offspring of that sire exhibiting about 3/4 of the diversity of the population. That's because the sire only controls 1/4 of the genetic variation. So if you line breed, inbreed, right, then you do see groups of offspring that are more similar. But to do that generally takes a relatively high degree of inbreeding. And more specifically, you have to be inbred at the particular loci, the spots in the genome that are responsible for variation in that particular trait. So it's possible to be line bred and see reductions in variation for one trait, but not for another because of that very thing. Point being, though, it generally takes a fairly high degree of inbreeding before you see that.
All right, thank you.
I would also make the point, though, not to get too hung up in uniformity, right? For seed stock producers, I understand the desire to have uniform groups of bulls for sale, but variation is actually your friend, because without variation, we can't make progress in the breed or progress in your own herd. So having variation, being able to find outlier good ones is actually a good thing. So I wouldn't be scared of variation.
All right, thank you. Next question here. Has there been any follow-up studies 2 or 3 years down the road on if the preliminary genomic enhanced EPDs have proven to be relatively accurate? If an animal was predicted to be 0.0 birth weight EPD following enhancement, what are the odds that sire sits near a 0.0 birth weight EPD after 1, 2, or 3 calf crops? We've seen some wild movement on a couple of sires after a little as 10 to 15 calves registered.
Yeah, good question. I'll answer that two ways. One, so larger, what I'll call validation of genomically enhanced EPDs has occurred that I'm aware of 2 places, and I'm sure more. One is IGS has done at least internal validation, and the way they do that is ask the question is what's the correlation between genomically enhanced EPDs and phenotypes versus traditional, if you will, EPDs and phenotypes. And the way they do that is they calculate the EPDs withholding some animals' phenotypes, so those animals that are withheld can serve as the validation. And what they've shown is for all traits that the genomically enhanced EPDs produce higher correlations, meaning that they're more accurate. More independent than that, the Meat Animal Research Center has done a similar exercise. And of course, US Mark on an annual basis shows regressions of offspring performance of bulls they sample in their GPE project, regressed on sire EPD. And the expectation of that is that the regression's 1. So for every 1 unit change in sire EPD, you get a 1 unit change in average offspring, whatever, birth weight, weaning weight, marbling, etc. And for the majority of breeds, for the majority of traits they evaluate, that is indeed the case. And so it tells me that they are more accurate. Now, to the wild swings question, 10 to 15 calves is actually a fair bit of information coming in. So particularly if the trait is moderately heritable, that's quite a chunk of data. We do, I guess what I'm trying to say is we do expect them to continue to move, because even with genomically enhanced, they're more accurate than they would be without it. But the accuracy is certainly far from being high. And so as we get more recorded calves in, you're going to see those EPDs continue to move. There's no doubt about it.
Right, next question. I just read an article where an expert said that producers should be using more terminal bulls. As I look at the EPDs of bulls that are being promoted and sold, most look like they're actually terminal bulls, very high growth, high carcass weight, and excellent carcass. I think the buyers are buying them to make females thinking that they are maternal bulls. Your thoughts on this?
So I don't know who the expert is, and I don't know if maybe that was me. But I do think there's value in commercial producers using more terminal bulls if they're able to either source replacement females off ranch. So in other words, buy them from somebody that has a more maternally focused breeding program. And so then that commercial producer can focus on only one thing, and that's terminal. And I think there's big advantages, particularly if the commercial producer is smaller in scale. They don't have to worry about managing a small group of replacement females. They can focus on doing only one thing. The other thing they could do if they're big enough is have a herd actually dedicated to making replacements with a totally different breeding objective. So I think that can make sense. I agree with your point, though, is across the majority of breeds, we've seen breeds try to chase post-weaning traits, post-weaning gain, carcass merit, perhaps at the sacrifice of more maternally oriented traits. I think of something like stayability. I also think of moderating mature cow weight. I wish I knew what the right answer was. It's a chicken or an egg thing. Seed stock producers would probably say we'd stop selling those terminal bulls if people would stop rewarding us for making them. But there is no doubt that commercial producers would be better served in many cases, not all cases, with either trying to clearly delineate between terminal and maternal in their own herd, or if they're not going to do that, if they're going to ask one bull to do all things, to find bulls that are far more moderate, particularly for things like mature cow weight.
All right, a follow-up to that asks, are we as an industry at a point where enough is enough with some traits like growth, carcass weight, and milk?
The answer is yes. So EPDs enable directional change, right? They work. But never did anyone say that take this EPD and select in one direction for eons, and that's going to lead to something that's more profitable. So there are intermediate optimums that are more economically favorable. That's why I'd recommend that people use economic selection indices to try to have a more balanced approach, and to think about things in an economic framework. I am concerned about mature cow size, in particular, because I think that a lot of commercial producers maybe focus on revenue and don't think about cost. And so that bothers me. I also worry for people that are thinking about profitability over a longer term time horizon, that sustained reproduction becomes very important as well. So I fully agree with you that there are intermediate optimums. And if we were to focus our selection decisions on profitability, we'd probably find middle ground.
Very good. Well, I don't see any additional questions. If anyone has anything that they would like to ask before we wrap up here this evening, now's your time to do it. All right. Well, with no additional questions coming in, Dr. Spangler, thanks so much for your time here this evening. To our attendees, thank you so much for sharing your evening with us. We hope we've answered some questions that you've had about DNA testing and genomics. If you have any questions, feel free to reach out. We are always happy to answer those.
Thank you.
All right, everyone have a good evening.